In this video, I'm going to explain, hopefully a little bit more clearly, about electrical potential energy. And hopefully you've watched the review of the gravitational potential energy, and you've seen these equations on the work done by an electric field, which is just the electric field strength times the distance through which the charge will move through the field times the size of the charge that's going to move through the field. And when we look at this, it looks very similar to the work done by a gravitational field, where the g is the gravitational field strength, r is the distance through which the field that we're going to move, and m is the mass of the particle that's moving through that field. With gravitational potential energy and work done by a gravitational field, m was the feature that was responsive to the field. In the case of electrical fields, it's q. That's the property that's responsive to the electric field. So the larger the q, the more responsive it's going to be. We also have the electrical field, which is just the force that's exerted per charge. And we have r is just the direction of the change in the position of charge. It's actually, that's not entirely correct, it's the change in the position of the charge, and it has the direction of the change in position of the charge. And here I have a familiar diagram here. This is going to be a 10-meter drop. That's this distance here. I have a charge q, which is going to be 10 to the negative 6th coulombs. And I'm going to put in an electric field of 2 times 10 to the 6th newtons per coulomb. And once again, just like the gravitational field, I'm going to treat this electrical field as being constant throughout all of space, at least all of the space that the charge might move through. So this charge is always going to experience that exact same electrical field. And so I can calculate how much work is done by the electrical field just by taking the responsiveness to the electric field, the size of the field, and the distance through which the field we're going to move. And when I multiply that all together, I get 20 joules, or 20 newtons per meter, as the amount of work that the field is going to do. Now this translates into a change in electric potential energy of negative 20 joules. And that's because we had the ability to do 20 joules more of work than we do at the end. So when it starts up here, we have the ability to do 20 joules more of work than when it gets to this point down here. So in the course of moving from the top to the bottom, we lose the ability to do more work. Now, this is all very similar and familiar to what we did with gravity, but there's a difference. With gravity, there's only one type of mass that we're aware of, which is positive mass, so positive attraction to other masses. But with electrical charges, we have positive and negative charges, and so some combinations attract and some combinations repel. And I'm not going to get into the interactions of charges. I'm going to use the field as my mediator here. And so I have this electrical field, and it's still pointing downwards. And remember what an electrical field means. It means this is the direction that the force would be for a positive test charge. But if I have a negative charge, which is the case here, then the force on the negative charge is actually going to be upwards. It's going to be in the opposite direction. It's going to do the opposite thing that a positive test charge would do. So in this case, in moving it from its original position to its final position down here, we're actually making it so it has a greater distance through which it can move in the direction it wants to move, because you can think of it, it wants to fall up. And we're moving it further this way, in the opposite direction that it wants to go. So we should actually get more potential energy out of this. And when I do the work equation, I get that we actually, the field, I should say, actually does negative 20 joules of work to this charge in moving it this direction. And so we gain 20 joules of potential energy. So hopefully this makes sense. Based on the gravitational potential energy, it's very, very similar. It's just that we're dealing with a different fundamental property of objects. Where things get a little bit more interesting is that with gravitational potential energy, with electric potential energy, those are all the results of interactions between charges. So I could write this a little bit differently. I've been discussing it in terms of the field. But we have this interaction. This is caused, oops, not quite sure why I did that. This electric field is caused by some charge or charge combination, and this is the charge that we're allowing to interact with those charges through the electric field. So this potential energy and the work done, it's a result of interactions. What we're going to be doing next is looking at a way to describe what happens independent of an interaction. Sort of like the electric field itself is independent of an interaction.